new dynamical phenomena observed in modern days quantum simulators. And the talk comes out of one pretty basic question. There are many systems that are realized in the lab. People try to perfect isolation and control of these systems. But now let's imagine that you have such a system very, very well isolated, and yet the system is still interacting. Right? Then there is a natural question. Is your long coherence time, does it buy you any new physics here? Or like, what can you observe? What can you do with your long coherence time? And if you have with our 1 minute coherence time, will it lead to observation of new dynamical phenomena or no? Right? And in order to answer this question or to gain basic understanding, right, we can look at analogy with classical systems, right? And in classical systems, we know that sufficiently complicated classical systems become rapidly ergodic, right? You have emergence of statistical mechanics, and even if you prepare a system in a crazy non-equilibrium state, all the non-equilibrium information is very rapidly erased. And now there is a quantum analog of such systems, so-called thermalizing phases. And I will discuss this a bit more details in the next slide. Of course, in the classical systems, there are exceptions, right? There are integrable systems which have higher symmetries, which have special integrals of motions, right? And these special integrals of motion prevent chaotic motion, right? And give rise to a stability and very different dynamical behavior. And it's not a subject of today's talk, right? But recently, many bidirectionalized phases were realized to be a direct counterpart of these integrable systems on the quantum side of this line. But the talk is going to be not about many bidirectionalized phases. The talk will be about something that kind of is in between here. And let me start with a somewhat pedagogical introduction, right? Just to show you ergodicity and notion of ergodicity in classical systems. It's very useful to just use this billiard, right? And put a ball ballistically bouncing in a billiard. And if you observe a ball, you see that after some time, ball has visited every point of the billiard, right? And from here, you can conclude that initial location of the ball doesn't matter so much, right? And eventually you equilibrate and have equal probability of observing ball everywhere. Now, integrable system, integrable billiard, you have markedly different behavior. You put a ball bouncing in this ellipse, and ellipse has a much higher symmetry, right? It has another lower conservation, and you see that ball doesn't visit every point of this ellipse, right? There are some regions which are actually never visited, and this is much more special motion, right? And there we need to know our integrals of motion to predict what is happening. Now, quantum systems are believed to behave in a similar fashion, right? But it's much harder to put a cartoon on a quantum system because their dynamics lives in a many-body Hilbert space. But the idea is that if you start with some isolated system and do the unitary evolution, of course, nothing can happen to your wave function. It was a pure state, it remains a pure state in the unitary evolution, right? Yet there is an intrinsic equilibration, and intrinsic equilibration occurs between parts of your system. So the idea is that the entire system remains in a pure state, yet quantum mechanics can afford that when the full system is in an entire state, all its subsystems are in a thermal state, right? So you calculate density matrix of one spin, of two spins, and all these density matrices are very close to your thermal density matrices. How is it possible? Of course, it's possible by entanglement, right? And here there is this famous eigenstate thermalization hypothesis, which suggests that in thermalizing quantum systems, eigenstates, already many-body eigenstates, may look thermal, and they look thermal exactly in this sense. The eigenstate is a pure state, but whenever you zoom in on any part of your system, you observe that your density matrix is thermal, your quantum expectation values of observable in the eigenstates are going to agree with the microcanonical ensemble, and something that is very, very important here, right, and I find it really surprising and somewhat puzzling, that we need quantum entanglement to become thermal, right, because again, it's a quantum system, its entire system is in a definite state, so uncertainty in subsystems may come only from entanglement with other degrees of freedom, right? And that's exactly by this entanglement, and by growing this entanglement, you do reach a thermal state, right? You need actually a lot of entanglement of these two spins with the remaining spins in order for their density matrix to look thermal. Because if it's a high energy state, it's expected to have a lot of entropy, and that all entropy comes actually from von Neumann quantum entanglement entropy, right? And that means that thermal eigenstates would have volume law entanglement. That entanglement would grow proportional to the number of degrees of freedom. Now again, coming back to the previous slide, it's a natural question, do all quantum interacting systems thermalize? And the answer, as I said, is no. there is at least these two distinct classes, right? There are these thermalizing systems, which would be a majority or general typical systems, right? They have very fast spreading of entanglement in a quantum quench. Their eigenstates would have a lot of entanglement, and they would obey against the thermalization hypothesis. At least people don't know any exceptions so far from this, right? On contrast, there is many body localized phases where entanglement grows much, much slower, logarithmically in time. Eigenstates are volume law, are area law entangled, so in some sense they look almost like a product states weakly twisted by some unitary, quasi-local unitary circuit, and there is quasi-local integrals of motions and can be used to characterize properties of this phase. But now again, the talk is not about this guy, the talk is more about what is possible in between these two systems. And the entire scope of the talk and entire credit actually must come to the experiment. Right? It was Lukin's experiment which realized a chain of Rydberg atoms. It was also realized before by other groups, but I'll concentrate for the sake of time on this experiment. And what they've done is they managed to trap a number of Rydberg atoms, I believe up to 50 or 53 Rydberg atoms in tweezers, and they shine a light onto these Rydberg atoms so that the light is resonant between the transitions. Now, if there are two Rydberg atoms next to each other, they become to interact. And this interaction, right, may make the transition off-resonant. And that's what is called Rydberg blockade. And the idea is I'm a theorist, so I ignore all the experimental complications. And for the sake of theorist, you can assume that this Rydberg blockade leads to a very weird condition, right? Each atom is a spin-half system, it has a ground state, excited state. And now Rydberg blockade, it prohibits to have two excited states next to each other. It's not that it prohibits it in reality, right? You can have two excited Rydbergs next to each other, but if you start dynamically from a state of no excited Rydbergs, you cannot get such a state dynamically, right? Because again, as I promised you, in this assumption, if there is a Rydberg here, this atom cannot be excited by your laser just because its energy level becomes off-resonant, right? We can make an approximation that the next atom already can get excited, and that's justified because the interaction decays very fast in distance, right? So the idea is that I want to operate in a regime of nearest neighbor Rydberg blockade, and I'm kind of ignoring effect of Rydberg interaction on the next nearest neighbor atoms and longer range. Right, that's very elegant system that was realized, and the puzzle that came from experiment is that some states in this system, for example, this Niel state, which would play a special role, have long time oscillations, and some states don't have any oscillations, right? They don't have any special dynamics and have much faster relaxation. And that, this experiment motivated us to study the model, and that's kind of all the words that were on the first slide came out in some sense from this experiment, right? So now, how do I think about this model? Well, again, theoretically, even Hilbert space becomes weird because of this constraint, right? If I think about two spins, right? Two spins have 4 states in a Hilbert space, but these guys don't have 4 states, they have 3 states, right? And 3 spins would have 4 states, I'm assuming periodic boundary conditions, and so on, and you can persuade yourselves that the size of the Hilbert space grows as a Fibonacci number, right? And that means that there is no tensor product structure in the space, and it's exactly because of this constraint, right? This constraint implies certain non-locality. If this spin is up, or if this atom is black, next one must be white, right? It's a certain non-locality that exists in this system. Now I can think about Hamiltonian in this approximation of nearest neighbor Rydberg blockade as very simple Hamiltonians. Basically sigma x matrix, which I simplify here as x, times 2 projectors, right? So it means that your Hamiltonian flips your atom if it can, right? If neighbors are in the ground state, you flip. If neighbors are in excited state, you cannot flip because you're off resonant. So very simple, very elegant Hamiltonian. Now you can if you like graph theory, you can actually use this Hamiltonian plus Hilbert space as a graph. Right? It's a very simple graph. You see that vertices are states, and whenever you have possibility of transition by Hamiltonian, so for example, in this transition, I can flip this one, right, from black to white. I draw a link. Right? So from this state, for example, I can kill 3 Rydbergs, but I cannot create any new excitations because of blockade. Right? So this guy has 3 connections. This guy, for example, has a lot more connections, right? Because here everybody is in the ground state, So I can create excitations anywhere where I want. Right? Very simple, elegant graph. Now, of course, in experiment again, you have 51 atom, you have much bigger graph, right, and many more vortices. And let me show you simulations of the physics that was observed in the experiment. Namely, you can simulate numerically what happens in a quench, right? I prepare different initial states, this initial state, this initial state, this initial state, and follow dynamics under this Hamiltonian, right? Hamiltonian is very simple. Flip your atom if you can, right? So what happens to this state? And first thing you can look at is entanglement growth. And entanglement growth for each state is linear in time, so that's as expected for thermalizing systems. But one surprise that you see is that slopes of this linear growth is very different, right? The zero state has very fast slope, this Niel state has the slowest slope. Moreover, for Niel states, there are some weird oscillations of entanglement on top of this slope, and there are weird oscillations of local observables which persist to very long times. If you try to do it on this state, these oscillations of local observables are going to decay around this time. So there is certain atypicality, right? The slope depends on initial state, long time oscillations are observed, and so on. But what is even more surprising is when you look at return probability. And by return probability, I mean really, in terms of the graph, right, the experiment would be prepare your state, you prepare your system on a given state in a Hilbert space, and observe a probability to return to the same state, right? And generally, if your Hilbert space blows up exponentially, that thing should rapidly go to zero, as it always does for all these quenches, and never go back, right? And that's indeed, for example, what happens for Z4 state. You see that for Z4 state, it goes down to zero, and then there is some finite size noise here, and that's how it should look. But actually, for other states, Z2 or Z3, you see that surprisingly, this guy revives up to whatever, 80%, and then a bit less. But that's something surprising, right? It means that the system is non-ergodic because system tries to spread over all of your Hilbert space, but then magically it manages to come back, right? And then does it again and again and again. But again, what is surprising is not that the system is doing that for all states, but that it does it for some states. And that was puzzling for us, and we tried to understand origin of these periodic revivals. And of course, if you think about eigenstates, right, these revivals must correspond to some unusual eigenstates of your system. And indeed, you very easily can find those eigenstates if you look at eigenstates of this Hamiltonian and overlaps them with your favorite product state. So you know that this product state has very unusual dynamics. You ask, how many eigenstates does this initial product state expand over? And you see that it expands, of course, over many eigenstates. Here I show overlap as a function of energy, but the main guys are few, right? And they are very separated from other states, and moreover, they have equal energy distance approximately. And that's immediately you understand that that would give you quantum revivals. Moreover, these states are very unusual in the other sense. Here I'm showing eigenstate entanglement entropy with respect to bipartite cup, and you see that most of the eigenstates at zero energy, there is a lot of eigenstates there, they have a lot of entropy, right? Their entropy is order 6, and it would be a volume law entropy, right? So it's as expected from eigenstate thermalization hypothesis. But now these 7 guys, they don't want to be here. By some miracle, they end up to be at the very bottom, right? So we have this very weakly entangled states coexisting with strongly entangled states. And that kind of brings a puzzle. How do they even manage to survive? Because as far as we know, the system doesn't have any symmetries, at least any global symmetries, right? I will come to special symmetries later. And in some sense, there should be something that protects these guys from hybridizing with exponentially many neighbors, right? There are exponentially many neighbors to these states, and somehow they manage to stay away from them. Right? This is kind of phenomenology of the model, right? And just for, for fans of eigenstate thermalization hypothesis, there is another pretty spectacular manifestation of its violation, right? Again, I promise that local observables obey canonical value, and you see that for most eigenstates that's indeed true. There are fluctuations. These fluctuations will get weaker for bigger system sizes. Yet these special eigenstates that I was discussing, they are kind of as far as possible from your canonical expectation value of your observable, right? So again, these are states which don't want to be thermal, don't like to be thermal, and manage to do it. Right? So how is it possible?
So Maksym,
yes.
This number of states for the system to become, when the system becomes large, becomes exponentially small relative to the other states?
Yes, exactly. But the trick is that this exponentially small number of states can be accessed via a product state. in some sense, yeah, if I would have some exponentially, yeah, if I have order 1 or order L, order system size non-thermal states, but I could never prepare them, I wouldn't care, right? But these states are super efficiently preparable via your product states, and that's what makes them observable in experiment, and that's what makes this whole physics interesting to explore. Right, so now let me kind of go to the first part of my talk, namely discuss explanation of the states in terms of embedded SU2 symmetry. And the idea is following. You can look at this graph, which is Hamiltonian plus your Hilbert space, and you may find some similarity between raising and lowering operators. Right? You may say, let me split my Hamiltonian into two parts, raising and lowering, or forward and backward, and one part moves you forward on the graph, another part moves you backward on the graph. Right? So the forward part basically tries to kill excitations on one sublattice and create them on the other sublattice, and vice versa. Now you see, okay, that looks like respectable for spin algebra, right? Let me compute them. And you compute them and you get something that smells like HZ, right? You get sigma plus, sigma minus, you compute, you get sigma z Pauli matrix. And you think you are like one step away from success in solving this model. The only hope is commuting, the only thing left is commuting them again and seeing that your algebra closes. But your algebra doesn't close. Right? So again, if you commute them again, that would be a proper SU2 algebra, but there is some guys hanging out there. You can try commuting them once again, those guys become longer and more terrible, and so on, right? So your SU2 algebra has failed. Okay, so that's maybe too much to ask for the full SU2 algebra in this model, and that's something that we realized somewhat later, right? Let's not ask for the SU2 algebra, let's ask for one SU2 representation in this model. That's much less again to ask, and how we do it? We ask for SU2 representation starting from my favorite state in this model. So I want to create a highest rate representation starting from this initial state. I act on it by my raising operator, and this raising operator, what it does, it creates one defect where it's possible, right? So it propagates one spin flip, if you wish, throughout this state. Okay, if you act by a lowering operator, it brings you back, because there is no other things that can go wrong. Okay, your SU2 representation seems to have a chance to work. You do it again, the gain works, and then at the third step it fails. So even your SU2 representation has failed at this point, but now you can understand why it has failed. It has failed because you can kind of, two defects or two spin flips can be next to each other, and then your blockade condition is not effective anymore, and things can go wrong exactly here. But now you understand that this representation fails actually in very rare cases, right? It fails only when these excitations kind of collide with each other or end up being very close. So actually it turns out that there is a hope of correcting it, right? Or mathematically what I'm doing, I'm measuring eigenstate, eigenvalue of HZ operator on all the states, and what I see is that this guy is an eigenstate of HZ, this one is eigenstate of HZ, but this one is not eigenstate of HZ, and that means that the third step is wrong. And it's not an eigenstate of HZ exactly again because of this configuration. Because here you see there is a Z guy dressed by projectors, but now for this atom, there are no black guys here, right? So projectors are not effective anymore, so I'm going to get a discrepancy order 1 in expectation value, right? So it's not an eigenstate anymore, my SU2 failed, but we shouldn't go home, right? We should try to fix it. And now we kind of know how to fix it. We know that my SU2 fails from interactions between spin flips 2 sides away. And that gives us some hope. Namely, you can write out this perturbation to the Hamiltonian, and if you, after a few pages of algebra, you can figure out that this perturbation can fix, or almost can fix, your second step of SU2 representation. Namely, it can fix this state to have the same eigenvalue under HZ operator as all these states, but now it's like, you fixed the problem in one place, but you got another problem, right? You fixed your wheel, but maybe something else is wrong with your old car, right? So now the problem is when holes are 2 sides away, because this guy has interaction when holes are 2 sides away, and it spoils this guy. But now you say, okay, it's imperfect, but still let me do analytically. I know the value of this perturbation, H2, it's some simple quadratic equation, there is the optimal value. You can do numerics and you see that this perturbation, which is 5%, it does magic to you. Because that's how entanglement grows without the perturbation. It's slow, but it's still fairly fast. And this 5% perturbation kills your entanglement growth whatsoever, right? On time order 30, your entanglement still barely departed from the axis, right? There would be non-zero entanglement here compared to 0 here, but still barely visible, right? And that's again, for specialists, that's in contrast to the perturbation. This perturbation was also proposed by Rydberg-atom, but they used a different value which doesn't give you anything special in terms of entanglement growth, right? Entanglement growth is a bit slower, but still quite fast. So now you say, okay, this perturbation of 5% already does a magic to you, but now we know there is a problem with holes 2 sides away, so actually we need to write the whole long-range perturbation, right? The idea is that here I made my spin flip interact with guys 2 sides away. Now let me make it interact with all sides from 2 to some distance r, and hope that this deformation can fix them all. Now at this point you give up analytically, at least for a while, and you try to use numerical optimization of this deformation. And then, again, results are pretty surprising, because without constraining, you get exponentially decaying coefficients, right? So the computer spits you numbers which are exponentially decaying with distance. So it tells you that the deformation requires very little interaction that is long range. And the longer range you have, the weaker is your interaction. We stop here because that's about your level spacing. Doesn't make sense to optimize coefficients further. Also, experimentally this is probably totally irrelevant for the modern state experiments. Yet this deformation does something really surprising to you, right? Because if you see with this deformation, your fidelity, now for the biggest systems that you can simulate exactly, revives up to 10 to the minus 7. Right? So you have nearly perfect fidelity revivals. Your entanglement growth, again, basically goes away. You have the biggest singular value, 10 to the minus 2 at most, and then it actually decays after that. So it looks like this deformation really made your model special. And now you can really check what happens to the special eigenstates, right? I was showing the special eigenstates that have a highest overlap with Z2 state. And what this deformation done to you? It disconnected the states from continuum, right? And all other states kind of went down. So basically what we managed to implement here, we managed to get one SU2 representation inside otherwise states which look ergodic and look thermalizing. Right? So we deformed the model, we deformed it weakly, and now from this state we can check that there is indeed a SU2 representation. You can check matrix element of this raising operators, they obey approximately your SU2 property. You can check that the spectrum is very well equidistant. Again, the spread between gaps is order of 1%, right? And it's getting smaller the longer range deformation you have. So it looks like, again, you managed to embed this SU2 representation, yet your bulk is ergodic in this model. Right? So if you look at all other eigenstates, they do have level repulsion, they have a level spacing ratio which goes to Wigner-Dyson value and so on. So again, it's like a hidden SU2 model doesn't have SU2 on the whole, right? But now there is this hidden SU2 which can protect a certain number of eigenstates. So
these equidistant levels include the lines.
Yes, they're responsible for, and again, again, this would be the perfect model, right? To have a perfect revivals, you need this deformation, or at least the conjecture is. In experiment, you don't have this deformation, right? But somehow something that I still don't understand, right? The norm of this deformation is, like 7%. It's really, really tiny perturbation, right? So in that sense, experiment is very, very close without any deformation. It's very, very close to this point already, right? And that kind of what gives you oscillations and what gives you these scars. Okay, so I'm done with my first part of the talk, but now again, I was dealing with eigenstates, fairly complicated object. Many people don't like eigenstates, right? Many people like dynamics, because again, eigenstates is in many body systems, they are not possible to prepare usually, and usually again, pretty terrible objects. So what about dynamics? And with this, let me come to the second part of the talk, and here hopefully I'll explain first the name of scars, right? And I was telling again a complicated story, but there is a simpler version of it, right? So complicated story is I'm starting on this graph vertex, I do my dynamics, I go to another graph vertex, I gain spread over the whole graph, and oscillate back and forth, right? That's my Hilbert space dynamics. Again, pretty surprising that you go back and forth between these vertices, but, but actually, really, if I don't think about Hilbert space, the dynamics is even simpler, right? I just have collective oscillations between two neon states. I have a collective radio oscillation. I have black-white, up-down spin, it rotates into down-up. and then it rotates again. Right? The only trick is that that's happening in the interacting system, and somehow this rotation is much more stable than, for example, rotation from down, down to, if I try to rotate from down, down to up, up, or some other state. Right? So now we can apply actually a variational principle, which is a simple apparatus. There are different makes and models, but in short, it's a machine which gives you quantum Hamiltonian, it requires some variational state, and then it spits you classical equations of motion. Right? There are many makes and models on the market. There is a dynamical mean field, one of the earliest, most ancient make and models. There are more exotic things, for example, some disentangling transformation, Gaussian variational states. I'll be using this one, invented by Frank Verstraete, basically time-dependent variational principle using matrix product states. And with this thing, right, I can use the following variational state. I want to do a mean field, but mean field is not a good idea in this system because of constraint. If I try to do mean field, I have a problem because two spins cannot be pointing up next to each other, right? And mean field doesn't know about it. So I have trouble. So actually what you resort to doing one-dimension two matrix product state. And this is nothing else but a more kind of glamorous version of your mean field in a projected system. Because here, what I have this upspin matrix, which is a sigma plus matrix. And sigma plus is a magic matrix because it squares to 0. So now, if in this matrix product state, if I try to stick in two upspins next to each other, Pauli matrix squares to 0, and this matrix product state spits you automatically 0 weight of your wave function. So basically, this is a mean field. You see there is only one angle. I have a cosine up, amplitude of spin being down, sine theta of amplitude of spin being up. They exactly add up to 1. But the only difference is that this matrix gives me constraint. Right? Of course, in addition to constraint, there comes non-trivial entanglement from this MPS, and it becomes more non-trivial. But it was original experimental paper and then later Harvard paper, which did MPS in this ansatz. And what they found a very simple system of equations of motion with a very simple flow. And in this flow, it looks like there is one very special periodic trajectory. And this periodic trajectory is exactly the one which brings you from one Néel state to another Néel state and then back and forth. And this periodic trajectory is something that actually gave name to quantum scars, right? And let me just briefly review the historical perspective on where these quantum scars come from. And they come actually from billiards, which is a much simpler system, much easier to imagine, right? I was using this billiard to show you chaotic motion. I was not exactly correct, right? Or I was kind of swiping under the carpet some things. Namely, there is a chaotic motion, and now I can do a quantum particle on a billiard. That's, your Mathematica does in 2 seconds. You take a Laplace operator with vanishing boundary conditions and ask for eigenstate number 10,050. And that eigenstate number 10,050 is going to look like this. Some random collection of plane waves. But then you notice that this billiard has a bunch of high symmetry properties, and it has some unstable periodic orbits. So for example, if you bounce ball vertically here, it's going to be bouncing forever. But here I launched it a bit non-vertically, right? At a tiny angle of about 1 degree. And you see what ball is doing here, right? It bounces, but it tries to escape your stadium, escape this orbit, and finally it escapes. Right? So this stadium has a bunch of high symmetry periodic orbits, but all these orbits are unstable. Right? And it turns out that these unstable orbits, they have a fingerprints in a quantum property. So now eigenstates of your Laplace operator on the stadium, some other eigenstate, maybe not number 10,000, but number 10,011, is going to look like this. And you see in this eigenstate, it actually doesn't look like a random plane waves. It looks like a standing wave between these two walls. Right? And you can think about the standing wave, right, as being a memory of this unstable periodic trajectory. Right? Semi-classically, you would launch a wave packet on this trajectory. It would go many, many times back and forth, interfering with itself, and only then it will decay. And that interference, right, over long times would be sufficient to have an eigenstate which is localized around your periodic trajectory with a high degree. Again, it has wave everywhere, but it's heavily localized here, right? And in some sense, it's non-ergodic eigenstate, right? It's an eigenstate which has a probability concentrated around your trajectory, in contrast to this eigenstate which looks uniform and homogeneous. And this quantum scars in the many-body model comes exactly from this analogy, right? There are special eigenstates that I was showing you in this quantum model. They have low entanglement, low participation ratio, which would be analog of concentration in a billiard, right? They are concentrated. I cannot draw you Hilbert space because it's awfully complicated, but you can measure participation ratio. And they have this constant energy separation, which is also reminiscent a bit of this finite size quantization. And most of the eigenstates are conventional, right? So now again, we just basically together, Harvard work can help us to make this analogy very explicit, right? And basically says that these special states that I was discussing, they're like eigenstates living near this periodic trajectory, and there is a majority of other states which look featureless and look fairly bad, right, or fairly chaotic. But now at this point, right, again, I'm not sure how many people in the audience have experience with dynamical systems, but if you show this stuff to anybody who does dynamical systems or classical dynamical systems, the comment would be, hold on, scars are very, very special. There is another phenomenon in dynamical systems which is much more common. What about this guy, right? What about mixed phase space? And that's the last part of my talk, where I try to show that these scars are actually a lot more general and go beyond the simple model. And this mixed phase space, right, in order to just to explain what it is, right, we actually have to apply the same machine, but now change your shape of pasta as it comes out. We change now to a three-side unit cell ansatz. So we have a different ansatz, we have a different output, we still have an output, a classical Hamiltonian system, looks a bit more complicated, some equations of motion. Now you can ask, how do you analyze these equations of motion? Like, looks terrible, gives some dynamics, what this dynamics is, how do you visualize it, right? People from dynamical systems know it. The idea is that these equations of motion give you trajectory in a three-dimensional space right now. There are three angles, theta A, theta B, theta C. You start from some point, and you would evolve. Now, there is this idea of Poincare map. Namely, you say that in order to visualize it, let me choose some plane, in, let's say, theta B being fixed to some value, and let me track where my trajectory crosses this plane. This way I have a discrete map, right? I start from this point, dynamics brings there, and so on. And now you can see that this map will easily distinguish chaotic dynamics from irregular dynamics, right? From chaotic dynamics, you expect that you go all over the place, right? And then you would see a collection of dots on these maps everywhere. If you have irregular dynamics, in contrast, right, you may imagine that you would always stick in the vicinity of some trajectory. And then what dynamics is going to give you a set of points which surround this trajectory, right? So I hope this visualization is helpful, right? Again, each time I track where I cross the plane, and if I'm regular, I would be always crossing the plane in some vicinity. Now this is the Poincare map of this system, right, that I was showing in the previous slide, three terrible equations of motion. This picture is much simpler to understand. In particular, this is exactly something that I was telling you. There is this Km tori, as it's called in a classical Hamiltonian system. Different colors, there are a lot of colors, mean different initial conditions. But you see that, for example, if I launch my system here, it would go all the way around and around and around, right, and it would be sticking here. And these regions, in contrast, have a collection of random dots, right? So it looks like some regular regions embedded into something that is called chaotic sea. And now we can try to understand, okay, this is a classical system, doesn't have to do anything with the quantum dynamics, right? Is it useful at all? And now what we do, we again use this Poincare section and start your quantum system on the initial state which corresponds to a periodic trajectory. And you see that this initial state behaves pretty nicely, right? If you started somewhere else, here, entanglement grows quickly, saturates. Here entanglement grows much slower, entanglement oscillates, fidelity revives, and it has all characteristics of scar, right? But now again, one surprise that it comes from this variational principle, from a regular region of your phase space, and it comes from the state which is actually not a product state. The initial state here is entangled state. So I must launch my system in an entangled state, and then it has a better dynamics than if I launch it in a product state. Okay? A bit better, right? Product state behaves a bit worse. This is green line. It would be up, down, down state. It behaves not as good, but it's still kind of surprising. Now you can ask, okay, how generic it is. Let me use yet another ansatz. Let me use two-block sphere ansatz, right? Let me introduce a mean field with a constraint with two 2 angles per Rydberg. So now I'm assuming that there is some Z field, magnetic field, and it gives me non-trivial phase dynamics. Again, you get equations of motion, you have very beautiful Poincare section, you still have a periodic orbit in the center of this big stable region. This is visualization of this periodic orbit, right? If you expect that you switch on magnetic Z field, which is also possible in experiment, you expect that your precession plane would tilt, right? That's what it's kind of doing, but now it's an interacting system. So in addition to tilt, it does some very weird loop around the south pole, right? So it's a trajectory which has some non-trivial topology, and actually quantum system follows this trajectory pretty well. So here, black line is a trajectory which never decays, right? You know, it's a classical dynamics, doesn't know about quantum system. Dashed line is a quantum simulation, ITBD simulation in an infinite system. And you see that, you know, it follows, it is damped, of course, entanglement grows. You know, your spin would go off a Bloch sphere because entanglement grows, but it would be very slow, right? You know, it would go off, you know, a time maybe order 100 or so. So it gives rise to a long time persistent non-ergodic dynamics. Now, some specific questions, again, maybe more for specialists, very natural question, how to tell trajectories apart. Because this guy shows there is trajectory not only here, but also there. There will be tons of trajectories in the system. So for this, we have another quantity which was introduced a long time before in a context again of TDVP, so-called quantum leakage. You can calculate basically a rate at which your system leaves your variational manifold. And that rate gives you an upper bound on fidelity. So this is a classical quantity calculated from TDVP. This is your quantum fidelity. It's upper bounded by this rate. And it also can predict you when deformation gives you more chaotic dynamics or when it gives you more regular dynamics. And finally, let me close this part by discussing what happens actually when I have a strong leakage, right? When my trajectory is so leaky that it doesn't represent my dynamics truthfully anymore, right? Because that's something that is not guaranteed, that your quantum system, you created yourself variational manifold and want to project quantum dynamics on it. But quantum dynamics, you don't control it, right? It may say that I don't like your manifold, I'm going to evolve orthogonally to your manifold, right? I'm going to leave your manifold after some very quick time. And that's exactly this leakage rate. This gamma t here, it quantifies after what time all the weight of your wave function disappeared from your variational manifold. And when it's very small, you see its logarithmic plot here, it's very, very good. You say that my variational manifold is excellent. But now when you deform your model, you rapidly arrive to a situation where your variational manifold is very crappy. Right? You see that your manifold, again, after time order 1, almost all wave function is gone from your manifold. And what it's doing, you don't know now, right? Because your manifold has nothing to do at that point with your quantum dynamics. Yet, it turns out that there is still some merit in this leakage, and this is an example of very chaotic model. It's transversal longitudinal field Ising model, right? Model people use to study thermalization. And we do a simple one-dimension 2MPS ansatz on it. We find the periodic trajectory. We do all this machinery, and you see that again, there is no miracles. Entanglement grows linearly, yet you see that in the point closest to trajectory, entanglement growth is slower, right? If you correlate this leakage and entanglement growth, you see that the weaker leakages, the less entanglement you have at late times. And that's kind of interesting, right? Because again, this chaotic model, people would say that, oh, it thermalizes kind of irrespective of your initial condition. And this plot shows that indeed your entanglement saturation value is the same irrespective where you start, right? It's a thermodynamics, you predicted to have entanglement consistent with your energy density. If I fix energy density, all lines go to the same things. Here, this shows entanglement of a 1 spin, 2 spins, and so on in an infinite system. But what is surprising is that saturation time is markedly different, right? If you start close to this periodic trajectory, your thermalization can be slowed down, even in such a chaotic system. Right? With this, let me just come to the summary of my system, of my talk. Right? So I was trying to tell you about 2 viewpoints on this quantum scars, right? As some embedded symmetry. Another one is a influence of periodic trajectories in a variational manifold on your quantum dynamics. You know, one question is actually, is it useful for anything? Already, it turns out that it is. For example, this recent paper in Science, which was creating GHZ states, was using scars as an effective pi pulse. So they were trying, pi-half pulse, they were trying to entangle basically two states, NL and anti-NL, and they needed a measure to check how much phase they accumulated between them, right? So they created this state, now they did a detuning, on one sublattice would give you a phase to one of these guys, so you would draw a phase, but now you would want some way to measure this phase, right? And in order to measure this phase, you would want something like pi-half pulse, and actually they exactly use the scar trajectory as a pi-half pulse. So turns out, again, I'm very happy to see that it's already something useful. Of course, there are interesting questions. Can you use this deformed trajectory to get even higher fidelity? Because fidelity of the scar, right, it's not perfect. Again, it's an interacting system, you don't have a perfect revival. So what it gives you one of the factors among many experimental imperfections that limits your fidelity. And something else, right, can we have other uses of this quantum scars beyond this naive pi-half pulse in a GSU preparation experiment? Something else that I would just like to show a glance. This phenomenon is also there in 2D. So hopefully soon people will have Rydberg lattices, and at least in a most naive square Rydberg array, you still have spectacular fidelity revivals. You can also describe it using variational principle, using now not a tensor network, but I would call it a tensor tree. So you can come up with a tensor tree where it's almost your square lattice, but what you have done, you've cut your loops, right? This would be your square lattice plaquette, but you see that I doubled this side into 2 copies. It's a bit a simplification, but that's something that allows you to solve the system analytically and figure out that indeed there is also a periodic trajectory and understand the property of this trajectory. But of course, very exciting question is about other geometries, right? 2D opens you a Pandora box of all possible geometries, right? You can have frustrated geometries, you can have triangular geometries, and so on, right? So that's very exciting, and that should be soon available as well online. Finally, there are also many other connections and many works by other people, connection of the scars to compatibility. These models have some weird zero-mode subspace. There are SU2 symmetric relatives pursued by Andrew Bernevig and collaborators. Recently, there were also quantum Hall-inspired models, so these models turn out to have some weird connections to quantum Hall systems on a cylinder limit. There are chiral clock models constructed which have these scars. Again, 2D Rydberg lattices are in progress. Finally, there are also different sources of ETH violation. It would be great to understand if they are related or no. These days, people use quantum scar name for everything that violates your ETH, right? I think the name is justified if there is some semi-classics behind it and if there is some periodic trajectories, but it would be interesting to understand if in these cases when people see confinement or when people do some fractons and have some other higher symmetries, if there is again a notion of semi-classical phase space in these trajectories. Something that is most exciting for me personally would be actually trying to push the scars into strongly entangled domain. That would be something interesting, right? That entanglement growth is irreversible. These guys have some entanglement oscillating back and forth, but can you actually push it to have not one bit of entanglement, but let's say logarithmic entanglement, and then it would oscillate back and decay? And of course, again, it would be interesting to find some other practical uses of this non-ergodic dynamics. Finally, as a last part of the outlook, there is also a whole field of a chaos in a few-body system, and there is a whole zoo of phenomena which happens in these few-body systems which have mixed phase space. Here I'm showing phase space of so-called kick-top from a classical book by Hake. There is again stability of perturbation in this region, stability to dephasing, there is different statistics of the wave function. There is a lot of different physical properties. If you put your system in this regular region or if you put it in chaotic, there are many, many ways how you can tell where you started. Now, of course, many body systems need a bit of a different language. And it's interesting what of these guys carry over here. It's also interesting to relate these guys. Entanglement growth, which is absent in these systems. Lyapunov exponent, which is present. And also this TDVP leakage. There has been other exciting work on this direction by Hood Altman, Andrew Green, and many others. And with this, let me just come to the very last kind of point in my talk, right? I showed this slide. If you want to carry out just a single message from my talk, right? Life is not as simple as this. There are these systems with mixed phase space here, and there are these systems with some sort of generalization of quantum scars or slow thermalization on this side. And knowing that this mixed phase space is very abundant here, I would say that this slowly thermalizing initial conditions should be also fairly common in thermalizing phases and in thermalizing models. With this, let me just close by acknowledging collaborators. Most of the work has been done by this Dima, Bayan, Zlatko, Alex, who is local, my postdoc at IST, and Chris, who is a student of Zlatko. Part about deformation and SU algebra was also done in collaboration with Harvard team, Ben Wei, Sun Won, Hannes Pichler, who I think will be soon moving to Austria, Misha Lukin. Finally, this is how our wood, not 25 kilometers, but a bit closer away from here looks. You're always welcome to visit. There are open positions at all levels. And with this, let me just show you conclusions and ask for your questions.
This 2D many-body scar seem intriguing. I mean, it's clear that like 3 tensor networks could give rise to that, but is it obvious how to kind of fill the tensors with meaning to get to kind of devise these models, or is that a non-trivial?
Well, I mean, I think Rydberg, right? If you do this tensor tree, it doesn't care about dimension, right? The idea is that you cut all your loops. I can do your D equal 10 and can predict your frequency, and frequency I think will be predicted correctly.
Okay.
But in terms of other models, right? I don't know, in a sense that it's a very good question, right? What other models would have it, and if something else that would also is puzzling me already for a while, if you can have some of these phenomena on frustrated lattices, right? Because that's obviously where things go wrong, right? Square lattice is a bipartite, right? So you know, if you have oscillation up, down, up, it's kind of obvious that it should carry over to the square lattice of any bipartite lattice, but doing it in frustrated lattice. That's I think another level.
Thanks.
So I have a question, maybe a bit something that I would like to discuss with you afterwards. We also looked at the graph that we had in the first part with the Rydberg blockade, but we split it up a little bit different. So we actually said that we have like flip-flop loops, which is where so you have like plus and minus. And we split it up differently to say, well, there is hopping, and then there is particle number change. And then actually we found that the particle conserving part fulfills very well a canonical ensemble, and the particle changing part we can do like a grand canonical ensemble.
I see.
So it's like we don't start from everything canonical ensemble, but actually grand canonical ensemble. So I was wondering if there's actually also an ETH theory extension to the grand canonical.
And in what sense do you mean grand canonical ensemble?
So usually you have particle conservation in the canonical ensemble, and if we add, so say that you can add, if we add a chemical potential, then you have a grand canonical ensemble. And we treated, so to say, the Rydberg excitations exactly like this. No? We said, well, the Rydberg excitations are the particles. Now we allow them to hop, and this we treat them as a canonical ensemble, and then each of these canonical ensembles is connected by a particle exchange. This is then a grand canonical ensemble, and this also works analytically. So
I mean, right now again, maybe it's better to discuss at the board, because right now my understanding is that that's also somewhat similar how you check your ETH, right? In some sense, you don't have, if you want to do some prediction for your observable, right? You need to extract your temperature, and you don't have a temperature in an isolated quantum system, right? So what you do, you measure your expectation value of energy, and you ask at this energy density, right? What temperature would you give the same expectation value of energy with your Hamiltonian? And that's how you deduce temperature. And after that, right, you just simply apply your ensemble, right, to deduce all local observables. And that's like the slide that I showed where like there was this prediction, right, and the special eigenstates were very far away from the prediction. So are you doing something similar,
yes,
or are you doing?
On top of this, you can then also look at the numbers, for example.
I see.
Stations, and then deduce the chemical potential.
I see. Okay, that's something. So it's like, as you're saying, there is maybe another conserved quantity which we are kind of ignoring in the sample, but this model doesn't have a particle conservation. So okay, so that's very interesting.
That's why it's a grand canonical ensemble.
I see, I see. Okay, so maybe we should discuss it again as a board because
Are there more questions?
Yes, so it's kind of related to the previous question. In your first part, you kind of asked the question, how do I have to change the system so that it has SU2 symmetry?
yes.
So did you also ask the question, what actually is the symmetry of the system? So what kind of Lie group symmetry do you have there?
Well, we try, yes, we asked that question, of course, because, for example, if you want to do level statistics, right, you must resolve all the symmetries that you know of. And it looks like the system doesn't have any other symmetry except the ones that you would naively expect. It has inversion, translation, reflection, right? They're all special symmetries which are there in any chain model. And it has particle Hall, but it's not like it's a symmetry which changes your positive energy states into negative energy states. But that's it. So in that sense, if you resolve the symmetries, you do find level repulsion, right? And namely, if you would overlook some other symmetries there, right? It's, you're never sure, right? But generally, level statistics would show off, right, that you are totally wrong, you forgot the symmetry because you wouldn't get a level repulsion, right? And we get a perfect level repulsion, at least as far as it seems from numerical data. So in some sense, I can never be sure that I didn't overlook certain symmetry, but at least level repulsion and some studies that we've done suggest that the model on the whole doesn't have anything exceptional except for, again, all your favorite special symmetries that are there in any chain. So, but this SU2, right, it's kind of hidden there, right? Because, what you've done, we've built it only for some subset of states, and other states, I think they're kind of pretty much outside of this SU2, they don't enjoy it, and the operators don't enjoy it, right? That's the main kind of signature, that it's a hidden one.
Can quantum scoring be also seen as a potential way of applying that to the qubit states so that it would prevent coherence?
I mean, it's so right here in Rydberg there is this fact that if you have this Rydberg interaction which you don't kind of control, right? Or you can control it by bringing them very far apart from each other, but then again I think you lose some other properties of the system. So in that sense, I think if you have a normal qubits, right, which are very well controllable, you better just make them non-interacting and manipulate them in that form, right? So in some sense, I would say that these scars can be useful for a system, right, where interactions, are there and cannot be so much tunable, right? Then you can ask, even in the interaction system, can I have some trajectories which are well protected from those interactions and don't get destroyed immediately? If you have ability to completely switch off interactions, do it, you'll be better off, I think.